Morning. Good morning to all of you once again. Today we will be continuing our discussion on complex analysis. On the last day we gave a brief introduction of complex analysis. So we'll just continue now. Do you have any question from the last day, guys? If you have any question from the last lecture, you can ask, otherwise we can start. And what about your Sunday test? How it's going? The first thing which we will discuss today is the Taylor series expansion. If you have an analytic function which is analytic in some region, we can expand it in Taylor series. Let's say we are considering, okay, so let's say if you have a complex function f of z which is analytic in some region like this, okay, so we have a region like this. The function f of z is analytic inside this circle which has a radius, let's say r, and centered at some point A. The radius is, let's say, r, and it is traversed in the counterclockwise direction. So write few lines. If a function, let's say f of z, it is analytic everywhere inside the circle. F of z is analytic at all points, and let's say this curve is C, inside and on the circle C. It means inside there is no point where the function blows up or becomes infinity. So if a function is analytic at all points inside and on the circle C, having center at z is equals to A and radius r, then at each point z inside C, the function can be expanded. The function f of z can be expanded in Taylor series, can be expanded as. How it is expanded in Taylor series? Let's say we are expanding the function f of z about z is equals to A, which is the center of this region C. So f of z will be f of A plus f prime A divided by 1 factorial z minus A plus f double prime of A at 2 factorial z minus A whole square, and so on. Let's say if you want to write the nth term, so this is the nth order derivative of f of x at x equals to f divided by n factorial z minus A whole to the power n plus order. This is an infinite series, so it will contain infinite number of terms. We have just shown a general term, this nth term. So you can also write it in a compact form with the help of a summation. So you see, we can write it like n equals to 0 to infinity n derivative of f of z at x z equals to a divided by n factorial z minus a whole to the power n. Or you can also do, you can expand this function at, instead of a, we can also expand it in at z equals to z0 also. So at a it will be z equals to z0. So you can write a more generalized formula. Let's say if f of z is expanded about z is equals to z0, then we can write f of z equals to n is equals to 0 to infinity f n other derivative at z is equals to z0 divided by n factorial z minus z0 whole to the power n. Okay. Nth term or n plus 1th term? Acha. Now in that sense it is n plus 1th term, because n is starting from 0, so one term is extra. Let me know once it is done. Good morning, Ajay, Deep, Rani. Okay, look at this problem now. The first few terms in the Taylor series expansion of f of x is equals to sin x about x equals to pi by 4 are. Can you solve this problem? So here a is equals to pi by 4, right? Or z0 equals to pi by 4. You have to expand f of x about x equals to pi by 4. So wherever you see a or z0, you put pi by 4 and tell me the answer quickly. This does not require any specific knowledge of complex analysis. Taylor series is a more general thing. And we have also mentioned this Taylor series while discussing Fourier series. That Fourier series can expand both kind of function, but here for Taylor series you need to have analytic function. Good morning, Murli. You did not tell me, guys, how is your Sunday test going on? Look, the kind of question you might have seen in the Sunday test. You see, when you actually solve it at the time of giving the test, you may find it difficult or unusual, but I am pretty much sure that once you see the solution, you might think that okay, this problem was not that difficult, I already knew the concept, isn't it? Isn't it happening with you after looking at the solution that you already was very much aware of the concept involved in the question? 9 out of 15 correct. Yeah, that is very good. 9 out of 15, it is a pretty much good score, but you can improve. You need to revise regularly. Okay, the more you revise, the more strong you will become, and that is why we have made this policy that in each Sunday test the syllabus will be the previous Sunday test syllabus also, that will include the previous Sunday test syllabus also, so that you be in a constant flow. There may be one question or there may not be any question from a particular topic, but the syllabus will include the topics as well. And most probably we'll take a session today at 7:30 p.m. discussing the Sunday test solution. Okay. Option B you are getting? Yes, option B will be the correct option. Let's see how we get that option B. So you have to expand f of x is equals to sin x at x equals to pi by 4 about. So you see, what was the formula? The formula of f of x expanded about x equals to pi by 4, the formula will go like f of pi by 4 plus f prime of pi by 4 by 1 factorial x minus pi by 4 plus f double prime at pi by 4 by 2 factorial x minus pi by 4 whole square, and so on. Okay. Now let us evaluate it here. The values of f of pi by 4. What will be the value of f of pi by 4? If f of x is equals to sin x, so f of pi by 4 is equals to sin pi by 4. So it is 1 upon root 2, right? Now a prime of x is equals to cos x. So a prime at pi by 4 equals to again 1 upon root 2. F double prime will be minus sin x. So f double prime at x equals to pi by 4 will be minus 1 by root 2. F triple prime minus cos x. So f triple prime at x equals to pi by 4 is equals to minus 1 by root 2. Option B, all of you getting very good. So just put the values. So if you take 1 by root 2 common, because it is appearing everywhere, so 1 plus x minus pi by 4 minus 1 upon 2 factorial x minus pi by 4 whole square minus 1 upon 3 factorial x minus pi by 4 square, and so on. We need not to know, because only the first few terms you need to know. That is matching with option B. Okay, let's move on. So one thing you notice, if it is, just remember this thing, if it is asking you to expand about, let's say z is equals to z0, So your terms will come as different powers of x minus pi by 4 or z minus z0 in this form. Na? Let's say if you are expanding f of z, let's say about z is equals to z0. So one thing is sure, that the terms will come in the form of z minus z0 the power of z minus z0, z minus z0, z minus z0 whole square, z minus z0 to the power 3 and so on. So you can just generalize it, that you will get terms in this power, some coefficient will be multiplied. So if it is asking you, like let's say expand it about z equals to plus 2, so you will get terms in terms of z minus 2, you know. If it is asking you to expand about z equals to minus 1, so your term in the expansion will come out xz plus 1. So I hope you understand this one. Whatever thing, whatever point will be given, so if z equals to z0 is given, that will be z minus z0, and this z0 is itself negative, then it will become positive. So I hope you understand this one. With this, let us try to solve this problem. Expand the following function f of z is equals to 1 by z minus 1 z minus 4 about z is equals to 2. So obviously the terms will come in powers of z minus 2, and that is obviously seen. And one thing you know, whenever, let's say in binomial expansion, when you expand this in an infinite series, do you know that this x is less than 1? Do you know this or not? Every time this x is less than 1. So here also, when you are expanding it in an infinite series, the term of the expansion, that should be less than 1, right? Z minus 2 should be less than 1, z minus 2 less than 1. Mod of z minus 2 less than 1, then only you can expand. Look at this problem. You have the function f of z 1 upon z minus 1 times z minus 4. You have to expand this about z is equals to 2. This is what we have to do. Now let us try to visualize that where does this z of z is equals to 2 lie. So if we try to plot, so this is y axis, this is our x axis. So z is equals to 2 means x is equals to 2. This is, let's say, 1. This is 2. So you see, whenever I say z is equals to 2, what does it mean? Z is equals to x plus iy, na? So equals to 2, it means 2 plus I times 0, na? It means you go along x axis 2 units and you go along y axis 0 unit. That is why whenever we say z equals to 2, you imagine it like x equals to 2. So if some complex number is added, then you will go to the along the y axis, otherwise there is no need. So this is 0, this is 1, this is 2 and this is 3. Clear? About z is equals to 2 means about this point. Okay, let's expand it a little bit more. So what would be our required criteria? As I told you, the expanding term like here z minus 2 or z minus z0, that should be less than 1. Can you say? So what does it represent? It represents the inside points of a circle whose center is at z equals to 2 and radius less than 1 unit. It means if I show you here, try to understand it very carefully. Understanding the concept is more important than just solving the problem, because mathematically you can easily solve the problem, but you need to understand the concept behind it. What does it mean? About z is equals to 2 means z minus 2 less than 1. What does it mean? This is a circle situated center at z equals to 2 and having radius 1 unit. So the expansion needs to be done in this region inside the circle, right? So inside the circle the function is analytic and you can expand it in Taylor series. Is it clear? So the function is analytic here. The way we consider the Taylor series for this region, here function is analytic. So let us now do this problem. So f of z is equals to 1 by z minus 1, z minus 4. So how we can write? We can write it in this way: a by z minus 1 plus b by z minus 4, right? And if you take this identity, then a times z minus 4 plus b times z minus 1, this should be equals to 1, yeah? And from this what you gonna get? You will get a is equals to minus 1/3. If you just put it through the identity, you will get a is equals to minus 1/3 and b is equals to, you will get plus 1/3. Can you get it? Just put z is equals to 1, then a will be minus 1/3, and put z equals to 4, then b will be plus 1/3. In this way you can get it, and hence we can write our function f of z is equals to, let's say this is positive, so let's take that b thing first, 1 by 3, so b times 1 by z minus 4 minus 1/3 1 by z minus 1. Can we write it? Now somehow we need to take this term, you need to bring the term z minus 2. So z minus 4 is there in the denominator. What you gonna do then? Z minus 2 minus 2. Can you write it in this way? Minus 1/3. Z minus 1 is there, so we can write z minus 2 plus 1. Then z minus 1 will become. Now you need to format it in this form, like 1 plus or minus x to the power n. In this format you need to bring it. Plus, there may be plus or minus, so here also there may be plus or minus. So if you want to make it let's say 1 minus something, what you gonna do? We have to take minus 2 common, then 1 by 1 minus z minus 2 divided by 2. Can you write it? Look, this condition should be satisfied. Look, z minus 2 is less than 1, so z minus 2 by 2 is also less than 1. So that is why we are taking this minus 1/3 1 by. So we can write it as 1 plus z minus 2, because z minus 2 is already less than 1 and it is in the form of 1 plus z minus 2, so we can keep it like that, no need to take common. This is equals to minus 1 upon 6. This becomes 1 minus z minus 2 by 2 inverse minus 1/3 1 plus z minus 2 inverse. So what you can expand? It is now in the form of 1 minus x to the power minus 1. So 1 plus x square plus x cube okay, we can just write it in this way. 1 plus x square plus x cube and so on, and minus 1/3 1 plus x to the power minus 1. So there will be alternate sign. So 1 minus z minus 2, then plus z minus 2 whole square, then minus z minus 2 whole cube, then plus, and so on. Understood? So we don't have a space here, so I am writing it here. This will ultimately become minus half, minus 1/6 minus 1/3, so minus half plus 1 by 4 z minus 2 minus 3 by 8 z minus 2 whole square, and so on, and that is matching with option A, right? Let me know if you have understood this very good problem. Look, the mathematical part you can do, you are strong in mathematics, but the concept you need to understand. Let me know once it is done so that we can move to the next question. Yes, Deep. Have you noted down, or any question if you have? Can you not differentiate simply? Can you differentiate it? That will be very much complicated, you see. If you just take derivative and do that, you see how things will go. You can try at home. Consider the real function f of x equals to 1 by x square plus 9, the Taylor expansion of fx about x equals to 0 converges for all values of x, except at x equals to plus minus 3, for x greater than 3, x less than 3, and between minus 3 to 3. Which one is correct option? Simple problem, just do it. You can use the basic condition I told you. Tell me which answer you are getting. So obviously here you have to consider term involving x. X minus 0 means x. So the expansion term will come out in terms of x only. One more thing, why this 1 plus x, let us say all to the power n, this x is less than 1, why this criteria should meet? This criteria should be met so that this infinite series converges, na? That is the basic thing. Not able to solve? You see, f of x equals to 1 by x square plus 9, and you have to expand about x equals to 0. Option A you are getting. How option A? For all values of x. is it? You see, f of x is equals to 1 by x square plus 9. So we can write it in this way, 1 upon 9 you need to take common, 9 1 plus x square by 9. So this is 1 upon 9 1 plus x square by 9 inverse. Now when this series will converge? This binomial series will converge only if this modulus of x square by 9 less than 1, है ना? That means modulus of x square is less than 9. So x square minus 9 less than 0. So it is a square minus b square formula, modulus of x plus 3, modulus of x minus 3 less than 0. Now as you can see, this modulus of x plus 3, this term is always positive, greater than 1. So obviously this term should be negative. So therefore modulus of x minus 3 less than 0 means mod x less than 3. Now if you look at mod x less than 3, how does it look? This is 0, 1, 2, 3, 1, 2, 3. So between minus 3 to plus 3, in between this, the series will converge. You can do it now. Mod of x, you can take it once you take plus x, another you take minus x. So x less than 3 and minus x less than 3. So x greater than minus 3. That is, it is matching with option D. Yes, Ajay. Is it clear to everyone or any doubt is there? For large x, the function tends to 0. But you see, Deep, why for all values will not be the answer? If you check the values of x very closer to like 9, x square, if it comes very closer to 9, then the function will diverge. So we have to apply the binomial series condition. From that condition we see that between -3 to +3 the function converges. Okay, let's move on to Lorentz theorem. Look, Taylor series you have done. Now in Lorentz series, here you mainly see the application of complex analysis. So in Lorentz series, what we observe, look, in Taylor series we consider a circle, and we consider that within the circle all the function is analytic. There is no point of no non-analytic point. But in Lorentz series, the region of being analytic is a ring shaped region. And how is that? Let's say we have an inner circle like this, an outer circle like this. So your function will be analytic within the annular region. So let's say you have concentric circles having center at x equals to a, and the inner radius, let's say, is r1 and outer radius is r2. So obviously you can see that r2 is greater than r1. Let's name this inner circle to be C1, the outer circle is C2. The function f of z is analytic within this annular region. So if I show you the annular region, it is like this. This region is your region where the function is analytic. This is the annular region. I should have taken a small circle, then it could have been drawn very easily. But anyways, just understand that the function is analytic in this annular region, not inside. So write few things, whatever I have just said, you just write. If f of z is analytic inside and on the boundary of the ring shaped region R. So this is your R, bounded by two concentric circles. Concentric meaning, you know, concentric means having the same center. Two concentric circles C1 and C2 with center at z is equals to a, this, and respective radii. Radii is the plural form of radius, r1 and r2, provided r2 greater than r1. So r2 is the outer radius. Then for all z in the region R, the Lorentz series expansion of f of z about z is equals to a will be. How will you write? So a special expression is there. F of z is equals to, there are two summations in this expression. One is n is equals to 0 to infinity an z minus a whole to the power n plus n is equals to 1 to infinity. You see, first one is starting from 0, second one is starting from 1, b1 divided by z minus a whole to the power n. The function is finite always. I think the function is not finite always. If you take x is equals to, let's say, 3i, then is it finite? Yeah, x is real or fx is real? Yeah, here actually the binomial, you have been asked the binomial condition. X equals to 3i you cannot take actually. It may be finite, but the value at one point may be finite, but you have to find out the condition of convergence. Now here you see there are two terms where an and bn. An is equals to 1 upon 2 pi I, although you may not require this value of an, but for the sake of completeness we are learning this. F of z divided by z minus a whole to the power n plus 1 dz, and bn is equals to 1 upon 2 pi I sum over, this one an is taken over c1, bn is taken over c2, the outer circle. F of z minus a whole to the power minus n plus 1 dz. Now just write few notes. The Lorentz is obviously we are expanding in this region R, so here it will converge. The Lorentz series converges in the region R. And number 2, the point at which the Lorentz series expansion is carried out should be the center of the concentric circle, should be the center of the concentric circles. So you just need to remember this expression which is written in green color. Later on we will introduce singularity based on this expression. Is it done? Can you move on? Give it a try. The first few terms in the Lorentz series in the region 1 mod z 1 less than mod z less than 2 around z equals to 1. Okay, let's do a little bit of correction, guys, in this expression, last expression. It is minus n plus 1, so the bracket will not be there. Minus n plus 1, so it is actually minus of, if it give bracket, it will be n minus 1, right? So remember this thing, minus n plus 1 without bracket. Option A. So about z equals to 1, you have been asked how it can be. If you are choosing option A, it means you can say it is expanded about z equals to 0, है ना? 1 plus z square is coming, so it cannot be the option, right? It may be z minus 1 or 1 minus z. Do you understand? Let's do this problem. One upon z minus 1 times z minus 2. So we can write it as 1 by z minus 2 minus 1 by z minus 1. Can you write it? You can do it like a by z minus 1 plus b by z minus 2, then you can find the value of a and b. Now this is a simple function, so we can directly write this 1 by z minus 2 minus 1 by z minus 1, you will get back this one. Okay, so if you see, if I take this term, look, 1 by 1 minus z, no issue in writing this. So it is containing a term z 1 minus z, so it is already being expanded at z is equals to 1 plus 1 by z minus 2. We have just interchanged and nothing done other than that. 1 by 1 minus z, let's keep it like this, and 1 by z minus 2, what you can do, you can write z minus 1 minus 1. So 1 upon 1 minus z plus, you see, if you take minus 1 common, then it will become 1 upon 1 minus z minus 1. One upon 1 minus z minus 1 minus z minus 1 inverse. It means 1 upon 1 minus z minus, what you can write, this is like 1 plus x plus x square plus x cube and so on. So this is 1 by 1 minus z. Look, it is now has come in the form of z minus 1. So we can do little bit of simplification. So minus 1 minus, have you done any mistake? Look, this 1 and 1 minus 1, so this is cancelling, so we have minus z, right? This one and this one is cancelling, so minus z, and minus, we can write it as 1 minus z whole square, then 1 minus z whole cube, so this will become plus 1 minus z whole cube, and next time will come minus, and so on. Option B is coming, right? Clear, everyone? y x, this is 0 1 2 3, 1 less equals to mod z less equals to 2, है ना. So z will remain between 1 and 2, -1 -2 -3. So somewhat a circle like this, no? Do you agree with me? Its radius is more than 1 but less than 2. That is the meaning of this thing. चलो आगे बढ़ते हैं. Let's move on. The Lorentz series expansion of the function f of z equals to e to the power z plus e to the power minus e to the power 1 by z about z equals to 0 is given by. देखो f of z equals to e to the power z plus e to the power 1 upon z. So about z is equals to 0, but if you see, if you put z equals to 0 here, not creating a problem, but 1 by 0, that is undefined. E to the power z, you know the expression 1 plus z plus z square by 2 factorial plus z cube by 3 factorial and so on. E to the power 1 by z, 1 plus 1 by z plus 1 by z square times 2 factorial plus 1 by z cube times 3 factorial and so on. The first one is the sum n is equals to 0 to infinity. You see z to the power n by n factorial, and here also it is 1 by z to the power n times n factorial, right? So we can write it n is equals to 0 to infinity z to the power n plus 1 by z to the power n 1 upon n factorial. Now as you can see, e to the power z is not analytic at z is equals to infinity. If you put z equals to infinity, this diverges, and on the other hand, e to the power 1 by z is not analytic at z is equals to 0. So e to the power 1 by 0, so e to the power infinity, that is diverging, and as a result the Lorentz expansion will be convergent if we exclude these 2 points. If you exclude, means if you take 0 less than mod z less than infinity, then for other values it will be convergent. So option C. तो यहाँ पे मॉड तो वैल्यू चला गया यहाँ से. Look, you will understand this thing more clearly. Let me give you a couple of more examples. Is it done? Missed plus sign in second step. कहाँ पे? Here. Oh, sorry. This is a blunder. Thank you for pointing out. Okay. Now let me give you some of the expression. Now if you understand this the next thing, then you will be able to understand all the things related to this expansion. Okay. So a problem is in this form. It's a standard problem, just for your concept clearing purpose. You have to expand an expression 1 by z square minus 3z plus 2 in 3 regions for, let's say, for 3 conditions. Number 1, when your mod z is between 0 to 1, 1 less than mod z less than 2. So these 3 conditions we will be taking, and we will see how the expansion changes. Understood? Then a comparative discussion will be done. So let's do the first one. Before doing that, let us try to write this expression in a simplified form. So we can do middle factor in the denominator. So z square minus 3z plus 2 can be written as z square minus 2z minus z. So z minus 1, another term will come z minus 2. So we can write it as 1 upon z minus 2 minus 1 upon z minus 1. So let us now take the first case, 0 less than mod z less than 1. Try to understand it very carefully. So here you can see mod z less than 1, no issue in this, your mod z is coming out to be less than 1. So you see f of z is equals to 1 by z minus 2 is there. So what you have to take common? Minus 2 you have to take common. If you take minus 2 common, what you get? 1 minus z by 2 minus 1 by, here what you have to take common? Minus 1, है ना, 1 minus z. So if mod z less than 1, so z by 2 will be also less than 1. So minus half 1 minus z by 2 inverse minus plus 1 minus z inverse. So this is equals to minus half. This can you expand 1 plus x square in this form. So we can write it in the form of summation. Sum goes from n equals to 0 to infinity z by 2 whole to the power n, and this one 0 to infinity z to the power n. So this is the required expansion. This one is clear, guys. Now can you do the next one? You have to follow this. Look, 0 less than mod z less than 1, it means mod z less than 1, this one. So we have incorporated that. Now here you see mod z is not less than 1, here it is mod z greater than 1. Yeah. What is the condition you are getting from here? Mod z greater than 1 and mod z less than 2. These two conditions we can obtain from here. So we have to bring such a term so that it becomes less than 1. So if mod z greater than 1, so we can write 1 upon mod z, it must be less than 1, and here mod z less than 2, so mod z by 2 less than 1. Can you write it? And for the third case, you see mod z greater than 2. So we can say that 2 by mod z less than 1. So in the expansion, this thing will come. And mod z greater than 2 means mod z is also greater than 1. So we can also write 1 by mod z less than 1. So let's take up the second case, 1 less than mod z less than 2. The second case, 1 less than mod z less than 2. So this gives us 1 by mod z less than 1, means in the expansion this criteria should be hold, and mod z by 2 less than 1. Now let us go for this f of z. What we have, f of z is equals to, let us start from here, 1 by z minus 2 minus 1 upon z minus 1. Now 1 by z you need to take out from here. So once again you can take minus 2 common. So you get 1 minus z by 2 minus, if you take minus 1 common, sorry, if you take z common, because you see z is not less than 1, so you cannot keep z. So if you take z common, 1 minus 1 by z. Understanding? Try to find out the difference between the first case and second case. Here we took out, here we did the expansion about z, because mod z less than 1, this criteria was there, but here this criteria is 1 by mod z less than 1. So that is why we have to keep a term 1 by z. And here you see z by 2, because mod z by 2 is less than 1. Is it clear to everyone? This one you need to understand very carefully. 1 minus z by 2 inverse minus 1 by z, 1 minus 1 by z inverse. So this will be your minus half 1 plus z by 2, z square by 4 and so on, minus 1 by z, 1 plus 1 by z, 1 by z square and so on. You can write it in the summation form if you want. N is equals to 0 to infinity z by 2 to the power n minus 1 by z sum over n is equals to 0 to infinity 1 by z to the power n. Is it clear to everyone? With this knowledge, do the third one. Can you do the third one by yourself? Give it a try. The third one, mod z greater than 2. Look, I hope the previous one is done. Third one, mod z greater than 2, है ना? So what you can conclude, that 2 by mod z is less than 1 and 2 by mod z is less than 1. So 1 by mod z will be obviously less than 1. No issue in this. So f of z 1 by z minus 2 minus 1 by z minus 1. This was the expression, है ना? So we need to take out 2 by z. So obviously you need to take z common from the first one. Then only 1 minus 2 by z will come. And here 1 by z you need to take. So here you take z equals, you take z common. So 1 by 1 minus z. So it is 1 by z, 1 minus 2 by z inverse minus 1 by z, 1 minus 1 by z inverse. So this is equals to 1 by z, 1 plus x plus x square plus x cube, so on, 1 plus x square plus x cube and so on, 1 by z, sum over n is equals to 0 to infinity 2 by z whole to the power n minus, acha, let's write 1 by z one by z to the power n. Acha, 1 by z is there on both terms, so 1 by z you can take common. So this summation can be taken out also. Sure, you can further write it now. This is a more compact form. So have you understood what is happening? Will you now be able to tackle these things? Are you getting confidence? Tell me. If I summarize this whole thing, what you have to do from the given condition, you have to find something. You have to find something which is less than 1. You have to find something which is less than 1, and in the expansion you have to carry out the expansion with the respect to that thing. If you look at here, mod z less than 1, so your expansion was carried out in this way, considering, look, if mod z is less than 1, so z by 2 will also be less than 1, and this z is less than 1. In the next case, 1 less than mod z less than 2, you see 1 by z is less than 1, 1 by z is less than 1, and z by 2 is less than 1. So in the expansion we are having these terms, z by 2, 1 by z. If it had, let's say, z by 3, then also it would have been worked, because if z by 2 is less than 1, z by 3 will also be less than 1, right? And the last case, 2 by z is less than 1. If 2 by 1 z is less than 1, 1 by z will obviously be less than 1. So you are getting the term in the expansion in this way. Any doubt anyone has? If not, then we can start a new topic. Should I start a new topic, or should we do on the next day? What do you say? Should we continue today, or you want it to do on the next day? Murli, what are you asking? 1 by mod z less than 1, explain how it comes. In which case? in third case? Where you use Lorentz theorem is used in this expansion, right? This 0 less than mod z less than 1, this denotes an annular region, na? 1 less than mod z less than 2, mod z greater than 2. So this denotes an annular region where we are doing the expansion. Next day, okay. Third case, you see, mod z greater than 2, so 2 by mod z will be less than 1. So if 2 into 1 by mod z is less than 1, so obviously 1 into 1 by mod z will always be less than 1, na? 2 times of something, if it is less than 1, 1 times of something would definitely less than 1, na? So this is a conclusion from this. Clear now, Murali? If you use theorem, the expression looks difficult. We are actually using the theorem, okay? We will discuss it on the next day. We are unknowingly using the theorem. Here you see, if you look at n is 0 to infinity, and here n equals to 1 to infinity, but if you look at the expanded term is in the denominator. So it is like you are doing the expansion of this thing with negative n values. Either you put n equals to 1, you get 1 by z minus a, n equals to 2, you get 1 by z minus a whole square, n equals to 3, 1 by z minus a whole cube. But here if you put n is equals to, let's say, minus 1, you get 1 by z minus a, n equals to minus 2, you get 1 by z minus 2. So it is effectively the range of n is minus infinity to plus infinity, okay. Now the Lorentz series expansion, there may be various things. It can give you only first few terms of n, it can give you first few terms of this term. This term is called principal part. On the next day we will see, depending on how many terms survive, we have different types of singularity, okay. So that we will discuss on the next day, otherwise it will be heavy for you, because these are little bit complicated concept, but overall it is easy if you understand systematically. The overall thing is easy. You see, this one we have done for like the theory purpose, but this a and b are not used in the mathematical derivation. Mathematical derivation, what is required is you need to find out something which is less than 1, where we can do the expansion, right? In all the problems we have seen, we are always looking for something which is less than 1, and we are doing the expansion. So revise this one at your home today, and on the next day we will start singularity of complex. We will come back to this Lorentz theorem again. Lorentz theorem is not over yet. Many associated concepts will be discussed from Lorentz theorem. So stay tuned, guys, and revise this one so that you understand it better, okay. So let's end the session here today. Thank you very much for joining the session, and like the session, okay guys. Bye bye, take care, have a great day.